Hello, y'all. Welcome to lesson 126 in my DP chemistry curriculum. Today we're going over reactivity 3.4.3. We will be discussing heterolytic fission as the breakage of a covalent bond when both bonding electrons remain with one of the two fragments formed. So we're going to use some equations as well to demonstrate heterolytic fission. We're going to use curly arrows showing the movement of electrons, such as those reaction mechanisms. Now, when we go about heterolytic fission, we're reminded of homolytic fission. So let's take a look at covalent bonds. When covalent bonds break, electrons in the bond must move because they're not between the two atoms anymore. So they have to go somewhere. So we learned about homolytic fission a couple units ago, and that was when the two elements were the same, usually. So in homolytic fission, electrons are split evenly, which, remembering, forms free radicals. Those incredibly reactive species that have led to the depletion of our ozone layer, especially with like chlorofluorocarbons and such. Now, the new one we're learning about is heterolytic fission. Using your prefixes and just knowing that usually one's the opposite of another, if homolytic fission was the equal or same splitting of electrons, heterolytic is going to be opposite or unequal splitting of electrons. Remembering fission also means split. So this is where both electrons move to one atom. Now, if they're moving both to one atom, this is always going to create an anion plus a cation. Because they were sharing evenly before, and now one atom has one more electron than it started with, and one atom has one less electron than it started with. So we're going to be creating two oppositely charged ions. So let's take a look at this in equation format using those red curly arrows that we're supposed to be using. So if we look at homolytic versus heterolytic, I'm just setting it up. In homolytic, our species X bonded to Y will turn into X radical plus Y radical. They can be the same, and so we're going to use that fishhook arrow representing one electron each. That's why it only has one barb in its hook. But in heterolytic fission, we're going to just move them all onto one of these atoms. So I'll use a double-sided arrow representing both electrons are moving, and we end up with X positive, which is now going to be a cation, plus Y negative, our anion, with a new lone or non-bonding pair of electrons. You'll notice that we've actually created a nucleophile over here, something that's an electron-rich species with that non-bonding pair of electrons. With this, we can kind of look at why this actually happens. Why do electrons move all the way to one versus the other? And the answer is probably more obvious than you expect, but really, electrons, electrons move to the more electronegative species. This is something you're going to notice a lot if you haven't already 126 lessons in. Electronegativity pretty much governs why electrons do any of their movement, and on top of that, all the movement of electrons is what chemistry is. So it once again comes back to electronegativity. Now, a couple examples that we can look at. We used a lot of chloromethane or chloroethanes in our previous unit, so we'll go ahead and look at that bond between a carbon and a chlorine. And I'm just going to leave those bonds hanging. When we look at this, we can recognize carbon's partially positive, chlorine's partially negative. So when this bond breaks, we're going to see our electrons move onto that chlorine, creating two ions. We're going to have our what we're going to refer to later on as a carbocation, carbon cation, carbocation, plus our chloride ion. So this is how we can um, assume that the heterolytic fission is going to proceed, moving to the more electronegative chlorine. Now, something that's a little less common, but we can still see it, is our carbon-hydrogen bond. This can also heterolytically split, and keeping in mind that now hydrogen is more electropositive and carbon is more electronegative. In this case, we're going to get that bond to break, putting the negative charge on the carbon. So we have a negative charge on the carbon with that lone pair of electrons, creating a nucleophile there. And in addition, we just end up with our hydrogen ion, maybe an acidic condition. So this is all you really have to know about heterolytic fission. It's a pretty short lesson today, but I hope this helps and have a great day.